Hello friends. So welcome you all to the 23rd session. So in this section we are going to see an actual implementation of a floating point processor. Okay. So we saw the floating point format in the last class. So this is going to introduce you to the actual implementation of a floating point processor, which is actually a family of part of ARM family, and this is one of the co-processors that can be connected to the ARM while building the system. Okay, if you are interested in adding the floating point capability to the chip that we are making. Okay, so here I am going to briefly talk about the different architecture classification and where does SIMD come, where does it belong to, and then what is a vector processor. A very brief introduction, because since we are going to talk about vector floating point processor, it is logical to make you aware about these vector processors and their advantages. Then we will go into the details of implementation of VFP and how we will see one example of implementation. A floating point is not a complete application, but a small implementation which will show you the different features of VFP. Okay, so the architecture, the processor architecture classification, actually given by a very 1965 time scale. This was done, and later processors they fall into different categories now, but this classification done by Dr. Michael Flynn actually gives you a broader view of where a particular processor belongs to. Okay, so this is called taxonomy. That is a branch of science concerned with the classification, especially of organisms, but here we are using it for processor architecture. And these are the 4 broad categories. Any processor if you see in the world, they will fall under one of the categories. Okay. So let us see what they signify. So SISD is a single instruction and single data stream. That means a CPU is there, okay, a memory. So it accesses a stream of instructions, and based on what the instruction wants, it accesses the data also, and then the processing continues. Okay, so this is the processor which executes instructions, and this is the control unit which controls the signals to the memory and how instructions and data are accessed, and then the data stream gets all the required data from the memory and they process on them. So if you see that a single processor, okay, it gets one instruction stream coming into the processor and one data stream, and it operates on them, right? So this is what is called a single instruction and single data stream processor. Any uniprocessor, including our processor ARM, falls under this category. Okay. Now what is SIMD? This is what actually we started off, because the vector processors, the vector floating point processor falls under this category. So what is the difference between that and this? Here the instruction stream that is coming from the memory, okay, is fed to multiple elements, processing units, okay, or we call as processing element. So if you see, there are n processing elements here, and all of them get the same instruction stream, but they get different data streams. They happen to work on different set of data. So though it is shown here as LM, M1 and Mn and different memory blocks, they all can be kept in a single memory, physical memory itself. Okay, it is not that they need to be separate physical memories, but they get different data. That's the main thing which you should keep in mind. But they all get the same instruction. So what you get, you will get a results which are equivalent to number of processing elements in the system. So if there are n processing elements, and this instruction whatever you is being performed is an addition, suppose, and if it takes let us assume that it is a floating point addition, and it is working on n set of data, n elements are there in processors. Okay, so you get after n, maybe this takes 3 cycles, assume. After 3 cycles, how many results will be available? N results will be available, because all of these processing elements run in parallel. So that is very important, because we cannot keep a processing element and they don't run in parallel, then there is no use. So all the processing elements are running in parallel, so they get the instruction and all of them operate on different data and give you a different set of results. So that's this is a multiple processing element. So it need not be multiple processors in a sense. It could be multiple add arithmetic units. Okay, ALU may be multiple add units may be there. Okay, and then each of them will be getting a different set of data. Maybe if you need to add, you need at least 2 inputs, and then each add units give you output. So the processing elements can be mapped to a add unit in ALU or maybe a multiplication unit. So there can be multiple units in the system and they all operate in parallel. Okay. Okay. So this is what is SIMD, and the vector floating point processor falls under this category. And another difference here, multiple instruction and single data stream. So what we saw earlier was single instruction and multiple data stream, and this is the reverse of that. What does it mean? You get different instructions to the units, okay, but the same data. When I say same data means it could be modified by this element and then the modified data stream will come. But if you consider this whole thing as a single system, there is only one data stream coming into the system, and then multiple processing units maybe pass on this same data, may be modified based on this instruction, and then a different set of instruction will be operating on it, and then the data element gets changed and then it goes out. A typical example is a network processor, where assume you have a router, okay, a network router, and then there is a input packets coming in, and then there are so many output ports, maybe input ports also many will be there, output ports there are so many, those packets may go into one of them. Now while these packets are getting routed, if you have a networking background, then you will know that some of the packets may get changed also, because based on the L2, L3 layers, maybe L2 layer will have the addresses different, because here the network is different from what network these packets come through, and then as per the L3, maybe in internet protocol, there may be some changes to the packet happening. You must be knowing that time to live is one of the element. Based on the number of hop nodes, the packets, the entry in the TTL may be changed. So what I am trying to say is the packets which get routed to different networks, they get changed, maybe at some level in L2 level, or maybe a packets data in the L3 level. So and then the processing also may work on, maybe this will work on L2 layer data, and then this may work on L3 layer, and this may do an encryption which may fall under the higher categories, and some elements may do a modification in the some layers. So different operations are performed on the same packet before the packet goes out. So as a typical example, okay, and then a very high level parallelism is called multiple instructions and multiple data stream, where you have multiple processing elements connected to network, or it could be in the same physical location, but they all work on they have their own local memory, or there could be a shared memory. So it could be a distributed system or a shared memory system, where each of the processing elements gets different data stream as well as different instruction stream. They work on different part of the data, and then but they all work on a single application, okay, but they may do different jobs which all combine together to achieve an application goal. So they all run in parallel, they all work on different set of data and different set of instructions are running on them. So this is called multiple instruction and multiple data stream. This is the network of workstation may fall under this category, okay. So this just to give you an overview, and then let us see what is SIMD processor. SIMD processor, and the name is a vector processor, or it could be called as array processor, and it runs multiple operations or a single add operation on multiple data, okay, simultaneously. That is very important, and it is common. It was common in 1970s and 1990s as a supercomputer. We call them a supercomputer, but now whatever the home desktop we have, they also may do a lot of jobs in parallel. So and all the PCs that we have is all multi-core processors, so they will be running in parallel. So now that these are 1970s 90s, they even having the vector processor was a considered to be a supercomputer. So operates on vector of data. So one example I can give you is a matrix, okay. Suppose you have n rows, okay, n and m column, so n by m matrix, and then you want to multiply it by another matrix, maybe m by p, okay. So when you want to do this kind of operation, matrix multiplication or matrix addition of n by n matrix plus another n by n matrix, if you want to add, I'm sorry about the squares what I see, okay, n by n. Now what happens, each element here needs to be added to this element here, okay. So we can take a particular row and then a particular row here and then add them all. So these operations which are done on a matrix, okay, they operate on different data, but the intent, either it is a multiplication or addition, that instruction is single. So basically a vector processor is to operate on matrix of data or a vector of data. So vector of data is maybe a single row or a single column element can be considered as a vector of data, and then corresponding elements are operated on either a multiplication operation or addition operation or any other operation that we want, scaling or rotation of matrix, anything can be done. So transformation, all these kind of matrix operations fall under this vector data. So an example is, suppose I showed you that matrix of data. Suppose we fill in those different data. Each vector elements are having some memory, and then we feed different data in the matrix, and then another set of vector processors, they also get a new elements, a row of elements. Then they all can do a parallel addition, and then the results could be shared in another vector. So typically in a scalar operation, one data, if in an addition operation, it's a one set of data is taken and then the result comes out. So whereas in case of a vector processor, a vector of data is taken, okay. So these two are inputs and then the output is given. So that means depending upon number of elements in the vector or number of processes that are running in parallel, that many the parallelism will be that. Suppose n processes are there, you get a n additions or subtractions or whatever will be done in a single cycle, or it could be, if addition takes 3 cycles, in a 3 cycles you may perform n operations. So this is the operation and the advantage of vector processors, okay. So just a high level overview of vector processor. So vector instructions access memory with known pattern. What I am saying is, you are giving a single instruction for a set of processors. So the organizing the instructions and the data is very important. So vector of data needs to be in a contiguous space, okay. So the memory configuration for a vector processor needs to be set up. Then only the accessing and the operations may be done with a higher performance. So all of you are aware of interleaved memory, where you have even our simple DIMM package of DRAM. These multiple chips will be there, and then we have data accessing from all the chips. So we are interleaving multiple banks of memory so that they all operate in parallel. The address resolution, resolving the address and then getting the data out. All banks in the memory will be working on in parallel, so you will get a performance benefit. So especially in a vector processor, we need data, multiple data to be fed to the processors. So we need a interleaved memory to feed the processor with more faster data, and the memory latency is amortized over multiple elements because we are accessing multiple elements at the same time. Data is accessed from memory, put in order into large set of registers. And one more thing we need to remember is, I told you that add unit, the ALU may be having multiple add units will be there. Okay, multiple add units, arithmetic units. But if they need to get 2 parameters each, then we need that many registers. Okay, so a vector processor will have more registers in the system. Okay, it also has more processing elements, the multiplication or arithmetic units, as well as more registers, so that the operands can be kept in them, and they can be accessed by multiple elements, processing elements simultaneously. Okay, and then they operate on the element one by one, and the processor writes the results back into memory. So this reduces the branch and branch problem because we are operating, we are getting results of multiple data operations, and then there are fewer instructions because one instruction itself does multiple operations. So there will be fewer instruction fetches. So these are the advantages of vector architecture. And then some other advantages: a single vector instruction specifies a great deal of work. Instruction fetch and decode bandwidth needed is dynamically reduced, because see, when the bandwidth is more is required, suppose the memory is not able to feed the speed at which the processor wants. Okay, now when I tell you that one instruction goes in and then multiple elements are there in the CPU, they work on the data in parallel, and then I am telling you that the data elements are arranged in a very unique memory, interleaved memory, and then they can feed the CPU. The instruction fetch need not be so fast. This speed of the memory need not be very fast, because we are getting multiple operations done at the same time with a single instruction. So it is dramatically, the instruction fetch and decode bandwidth is reduced. Results computed by various elements in a vector are independent of each other. One more thing we should remember is, in a matrix multiplication, the multiplication done by multiple elements, what you see, they are all independent elements. There we add them. So there is no data dependency among them. That means we don't have to wait for this operation to be completed before this can start. They all can start in parallel. So the data dependency or the data hazards what we have seen, in the uniprocessor systems are reduced. So still there will be a data hazard between vectors, but within the vector there is no data hazard. So it is power efficient because reduction in instruction bandwidth and the data hazard checking. So if you need to check the data hazard on every arithmetic operation that you perform, then there must be some digital circuits kept in the system, but which will consume power, but that is reduced. So we get the advantage of power efficiency because of the less reduced instruction bandwidth, and then reduced data hazard verification while running the code. Fine. So this is a very quick recap of what is vector processor and what is a SIMD architecture. So vector processor in a nutshell falls under SIMD, that is single instruction multiple data architecture, and it gets a single instruction, but it works on multiple processing elements are there, and they work on multiple data and produce multiple results. Okay, so it's a parallel architecture because more elements are there in parallel. Okay, are running in parallel. Okay, now let us see a VFP architecture. VFP is your vector floating point architecture. Now the vector floating point architecture is a co-processor extension to the ARM architecture. So now you should remember all that I mentioned about co-processors. Okay, so VFP is nothing but a co-processor. So this is data bus, okay, memory, this is address bus. Okay, so what is connected? The data bus is connected, and then if you recall, let me just quickly recall the NCPI coprocessor instruction, and then there are two this is the one input coming from ARM. There are two, CPA, CPB, if you remember, coprocessor absent and coprocessor busy signal. So all this handshake, and then there is no restriction that this cannot drive the address bus, but it can take the data in, and then it has got its own instruction pipeline which will be in sync with the pipeline in the ARM. All that should come in your mind. Okay, when I am talking about VFP, it is basically a coprocessor with using a CPID. Okay, let me just tell you now itself. CPID 10, it's not 16. CPID 10 and 11. There is a single precision floating point and this is a double precision floating point. So it uses the CPID of 10 and 11. These are all reserved. Okay, so it is not, it's a standard that it is used by vector floating point processor. That I don't call it as a reserved because the 8 to 11, if I remember, I think they are all given for user level with floating point processor or any other coprocessor that you can decide. So the coprocessor ID can be anything, but the 10 and 11 are used for by this vector processor, which comes along with the ARM SoC. Okay, ARM IP. So it works with ARM on VFP. So as a coprocessor. So you should remember all the instructions that it can operate on, and so basically all the operations done by vector floating point processor is done through a coprocessor instruction. Okay, so please remember this, all of them what I mentioned in the earlier class. It provides single precision as well as double precision. So this also you should know. Single precision is the 32-bit floating point representation, and double precision is a 64-bit representation, IEEE 754 standard. So it can work on any of them. So based on the type of the VFP we have. So just now I introduced you vectors, two vectors. So VFP has 8 elements. Okay, that can be done in parallel. See, this number cannot be arbitrary because it is tied to the vector length. When I say vector of data, a processor can operate on. Okay, I am saying that 0 to 7. That means 8 elements can be there. When I say that it can work on 8 set of data in parallel, that means that many processing elements should be in the system. The VFP that has been designed, okay, VFP need to have that many processing elements to process the multiple data elements in parallel. So this 8 is fixed. That means it can work on either 8 single precision operations or 4 double precision. Okay, because basically for the double precision is a 64-bit data and this is a 32-bit is a double. So the processing elements are operating in parallel. So please remember, this VFP can work on vector of data. It doesn't mean that it can't work on scalar data. What I mean by scalar data and vector data means, scalar data means maybe a single register operating on a single R2 and R3 and then putting the result in R1. It's a scalar data. Okay. When I say vector data, it is a set of registers which are identified. Okay, and it works on that, and then in another set of registers the results are written into. Okay, so this is the vector of data. So vector of data means the data has to be stored in some intermediate registers. So the registers are used for that purpose, and then the vector processor operates on those vector of data, and then results also should be a vector of data, because if it is operating on two vector operation, two vectors, and then it is a vector operation, then it will result in a vector of data coming out. So we need to identify the set of registers for where this result should be stored into. So most arithmetic instructions can be used on these vectors, most arithmetic, okay, and allowing both single precision, single instruction as well as SIMD parallelism. So it's essentially single instruction and SIMD parallelism means it's a single instruction is operating on multiple data. So the vector of data. Okay. So further, the floating point load and store instructions have multiple register forms. So even the ARM has multiple register forms, LDM and STM, which you have heard about. So floating point also supports, floating point processor also can load a data from the memory. Multiple words can be copied from memory to registers in the floating point processor, or it could be the other way. So the registers could be saved into memory. Okay, multiple data transactions can happen. Okay, now I told you that VFP has a double precision support also. So that is indicated by the naming convention D in it. So if suppose by if you come across VFP V version 1 D, that means that it has got a double precision support also. So whenever there is a double precision support, implicitly the single precision support is also supported. Okay, you can't say a processor with only double precision and not supporting a single precision. So, but the other way around is true, possible. Means if it is XD, that means only a single precision is supported. So what happens is when the processor supports both D and single precision and double precision, that means there is a complex circuitry in the system. So to perform these operations, whereas if it has single precision data, because the data width is lesser, then the processing elements complexity also comes down. Okay, that is very natural. By default, double precision support is also present. Okay. Now, what is the internal organization of the VFP processor? As I told you, VFP is connected to the data bus where ARM is also connected to. Okay. So VFP cannot exist alone. It's a co-processor. Please keep in mind. You can't have a system with only VFP and write some code for it. No, there should be an ARM in it. Okay, and then this coprocessor can be an add-on to that. Okay, and then with the help of ARM, coprocessor can do its job. Okay, so the data bus is common for both getting a data from memory as well as instructions also from memory. So if it is an instruction, it is fetched by this instruction issuer, which tracks the pipeline of FPU and then keeps track of ARM's pipeline so that they are in sync, and then based on the instruction, if it is a LDM or SDM, okay, then it activates this load store unit so that the addresses will be generated by ARM, and then the data coming from the data bus from the memory can be either transferred into the register or it can be copied back to memory. So this unit takes care of interacting with the memory unit. Okay, and then these three signals, you should be by now you should be concerned with that. This is NCPI, and these two are CPA and CPB. Okay, which is going to the ARM processor. This is a handshake with the ARM processor. This is a coprocessor interface. One thing what you should see from here is the arithmetic unit and register banks are connected like this. What does it mean? I told you that vector processor need to have more registers. So I will show you in a short while how many registers are there in the vector processor. But if suppose I tell you that there are some more registers, we can have a set of registers getting loaded from the memory while a set of registers are operated on using the arithmetic unit. So these two can happen in parallel. Okay, and similar to ARM processor, maybe the data is copied and then from the registers, and most of the operations in the vector processor, especially multiplication, division, okay, and then square root computation, all those, especially these two, takes more cycles to execute. So while this is being executed, okay, if there is a pipeline of instructions, I told you in the last class that FIFO of instructions can be in the system in the coprocessor. So if there is a FIFO of instruction, then already one division instruction has come and then it is being handled by this arithmetic unit, and then there can be a load or LDM or STM can happen in parallel because this can do that job. Okay, so parallelism is possible because of the number of registers that are supported in the system and then the way it is organized. So the as it is shown, the register bank has got more read and the write ports, and they can because of number of registers are more, one set of registers can be getting loaded from the memory while the other set of registers are operated upon with the by the arithmetic unit. So they all can happen in parallel. Okay. within the VFP. Apart from this parallelism, within VFP, ARM is also executing some instructions. Okay, once it hands over the CDP instruction, that is co-processor data processing instruction, like mul or add, whatever, it goes ahead with the ARM instruction. So it is also executing some control instruction in parallel. So there is a lot of parallelism now you see, and within this, when they have a vector of data, the vector of data is also doing a parallel operation. Not only the parallelism between these two, within the vector there is a multiple data elements are getting operated on. So there is a parallelism here too. So you can imagine a parallel execution between ARM and coprocessor, and within coprocessor the load element and the arithmetic unit are running in parallel, and then within the arithmetic unit a vector of data is getting operated on. Maximum I told you 8 single precision operations can happen in parallel. So there is so much of parallelism now in the same clock cycle, so much of operation getting done. So all these things keep in mind at the back of your while reading this, back of your mind, keep this thing so that you understand that how much of performance improvement you get with this kind of advancement in the architecture. So the load store unit operates concurrently, which I already told you. So and then the arithmetic units can work on the previously loaded operands. Hardware interlocks protect against data hazard. So that if I told you that between two vectors there can be a data hazard, but not within the vector, right? So there are some hardware interlocks. That means suppose there are two vector operations, and then if suppose I'll give you an example. Add is add two vectors. Okay, I will give you exact syntax later. Okay, in the class. Two vectors are getting operated, and then you say mul is also getting done. Now this vector maybe is used here as a one of the operands. Okay, between two vectors there can be a dependency. So the data hazard can happen. So the operands which are there in two instructions which are within the VFP which are getting operated, you can see that maybe S3 is in both the places. Then this has to write into the register first, and then this has to take. So the operand needs to come after the completion of this, then only this operation can start up. So that kind of a data hazard dependencies can be caught with the hardware interlocks in the system. So there is a support for identifying those kind of data hazards. Okay, now let us see what is the support code. So again I have to give you a little bit of background. Okay, again similar diagram. I am ARM and a VFP. Now I will not talk about just a coprocessor. It's a VFP coprocessor. Now if you recall IEEE 754, the floating point floating point format, it has got lots of exceptions. You have seen that. 0 by 0, okay, infinity by infinity. There are so many kind of operations which can result into some exceptions. Okay, there could be a data abort, or it could be an error, or there may be a possibility that the result that you are getting is going below the normalized value. You are getting a very low value. Okay, this is 0.0. Okay, and then you are getting a result which is very low, and then it has to be either written as minus 0 or plus 0. Okay, so that decision has to be taken. So this kind of data dependent exceptions are multiple possible with with the floating point arithmetic. So when such things happen, how does the vector floating point processor can start give a control to exception handler? I have to give you a little bit of background because it will be difficult if you don't have this in the back of your mind. Okay, now assume there is some floating point operation which was done by the processor. Okay, let me choose another color. Okay, now this has done a job. Okay, some floating point addition operation or maybe a division. Okay, let me call floating point division it did, and then they divide by 0 has happened. Okay, divide by 0. Okay, so any number some n divided by 0 has happened. So this has to be handled in a separate way. It depends on the application. So now See who executed this instruction. fdiv instruction was done by the vector floating point processor, but it has encountered an error condition. Now it should take it should bring the whatever has happened into the vector processor. It should bring it to the notice of ARM. Okay, so exception handler, how does it work? Okay, you know that vector table is there, intervector table, which is in the memory. Okay, suppose this is a memory, intervector table is there, and then maybe a undefined exception, undefined instruction. Okay, undefined exception has to be generated. Now that needs to be signaled to the processor, so that whatever the ARM processor is currently doing, it stops that and then gets the control to the intervector table, where undefined instruction instruction vector is picked up, and then the handler which is stored in the memory is executed. So something happening here needs to generate an exception, and that needs to be controlled, or it needs to be processed by the ARM processor. So please remember, VFP or any other coprocessor in the system do not have their own exception handling capability. So there need to be any exception handler specific to the particular coprocessor needs to be integrated into the ARM's coprocessor, ARM's exception handlers, and then based on which coprocessor or which instruction has caused the exception, accordingly the handler can act on it. Now how you may wonder, okay, instruction handler is called, okay, and then if you recall, while the instruction handler is called, it will also know which instruction has caused it, because see, the instruction is getting executed and then some other instruction is there. So you have to trace which instruction has caused the exception, and then process on that. So specific to the particular coprocessor, handling has to be done. So the job of the support code is to provide that capabilities. Okay, whoever is supplying the VSP, the vector floating point coprocessor, will also provide the support code for it, the exception handlers, and then the system software developer, okay, while developing the software for this whole SOC, will integrate those exception handlers which has been given by the VFP vendor into their application, and then build the system. Okay, so that's how it works. So that software component is called a support code. The support code provides a feature of IEEE compliance that are not supported by the hardware. So basically, if you can see that the support code is a software, because it has to be executed as a part of exception handling. So if a VSP processor in its own hardware, if it cannot take a specific exception condition in the hardware, it may be reason maybe that it is very complex to implement in hardware than putting it in software, or it could be that it's the probability of that particular exception happening is so less that we don't want to increase the footprint of the processor with a more complexity, or it will be very power hungry also if that there is a system there. But those occasional things can be handled using software without any performance drawback. If the application warrants that, then that particular handling of those things can be given to software or a hardware. So it's actually a implementation choice whether a handling of particular thing has to be done by hardware or software. But if it has to be done by the software, it has to be provided by the VFP vendor as a support code, which is called sub architecture. Okay, so the definition of the interface between vector floating point processor hardware and the support code is known as the sub architecture. So implementation. Okay, this is the definition of support code. What I mean by support code, and then I told you earlier, CP10 and 11 are normally used for VFP coprocessor. One is for single precision arithmetic and another for double precision. In general, this is a single precision and CP11 for double precision. So what I mean by that, suppose if you are interested in giving a set of data, the ARM core, okay, when I say you mean the ARM is giving a coprocessor instruction to the VFP, it may say that CP10, okay, I think 8 to some number, I think 11, I think CPID will be put right in the instruction format. So the ARM processor or the assembler or the compiler generates the code for the CPID based on whether a single precision operation has to be done or a double precision operation has to be done by the VFP. Okay, so based on that, the particular coprocessor instruction will be generated, and the VFP will look at the value of CPID, and then it comes to know whether it is supposed to do a single precision or double precision operation. Okay. Let us see. Now, what are the applications that will be benefited by the VFP, the vector floating point processor? Image processing applications. So let me give an example. What is scaling? Suppose you have a cube, okay, in a graphics world, okay. So you want to scale it to the bigger size, okay. So what is being done here in a typical image processing? Every pixel, suppose this is occupying a less number of pixels, and then this is getting a enlarged because of scaling, maybe scaling by 2 factor. Now whatever images are here are represented as 2 bits here and 2 pixels, and then they are expanded. So to do the scaling operation, a scalar vector has to be multiplied with the pixels in the system. Okay, there's a complex graphics, it's not very simple, but when you want to do a scaling operation, it's actually a multiple part of the images are handled, and then they can be done in parallel. Okay, image processing actually gives you a lots of scope for parallelism, because what you are working on this image, the same logic can be applied on this part of the image. Both can happen in parallel because there is no dependency among these two in terms of scaling. In particular, this gets expanded to this part, and the other part will get expanded to this part. So basically, these two part of the image can be acted on in parallel. So it is a good candidate for a vector processor. Okay, because multiple data, the same scaling factor is a single instruction. Okay, so that's a correct fit for a operation. Now 2D 3D transformation, suppose you want to transfer a 2D image to a 3D, then you have to give the depth perspective to them, or one more dimension has to be added. So these kind of things can be graphics or image processing are the good candidate for SIMD or floating point operations. And font generation, different kinds of fonts, maybe converting from one kind of font to the other one, okay, can be done. Digital filters, there is a serial processing algorithm which operates on parallel data, okay, and it is all, if you see, they are all if you want a good precision of data, it has to be done in floating point. Okay, that is a common thing. You can't achieve the same kinds of perfection in the image generation if you use a integer data format. So you have to have a floating point format so that the images quality and the quality of digital filters that perform a job on signal processing, they will also be producing a good result when you operate on floating point number system. So this is the better choice for performing these jobs. So any scientific application that needs floating point operation will be the VFP is the right choice. Okay, now we have enough of good background and why we need a VFP, how it is implemented, how they are connected to ARM, and okay, how they handle some exceptions also I gave you. But now we will see inside of VFP, what is inside of it. So basically, first thing what you should want to learn about any processor is its own registers. So it has got 32 general purpose registers. Okay, if you recall, in the ARM there were 16 general purpose registers. Okay, apart from bank registers there were 16 R0 to R15, correct. So maybe if you add all the bank registers and the SPSR and CPSR, it was coming closer to this. But here in vector processor, we have a 32 general purpose registers. As I told you, vector processor are working on vector of data, so they need more registers. So there's a natural choice is to have more registers in them, and the registers can store either single precision or a 32-bit integer in them. See, one thing you should remember, when you have a 32-bit register, this is a bit pattern. Okay, so either we can store a floating point value or an integer, okay, signed integer or unsigned here, because whether you are storing a floating point or integer depends on how you interpret this bit pattern in this register. Okay, there is nothing special about it. Okay, how do you interpret the numbers? How this now ones and zeros in the 32-bit values are interpreted depends on what kind of value you keep it in the register. But for a register to store some 32-bit value, or it's not only restricted to register, even a memory, it can store the bit pattern in the memory. How you interpret depends on what you know about this data, whether it's a floating point data or integer data, you interpret it that way. So this VFP registers are not aware, okay, whether it is storing a floating point value or integer value. Now there is a confusion. Now how will I know what is being stored there and how do I operate on it? So who decides it? It is decided by the instruction. Please remember, as an application developer, if you are writing assembly code, you are writing the instructions and you are moving the data into the registers, because you are only writing the LDM instruction from the memory. So as a programmer, you are supposed to know what data you are moving into the registers and what instructions you are giving to operate on those registers. Suppose if you move integer values from memory, you can execute some integer arithmetic on this, or you can even why do you want to do a integer arithmetic in the VSP registers? You can as well do it in ARM processor. So what I'm saying is, you can interpret it in a different way, and you can convert this integer to floating point and then operate on it internally in the VFP, because input may be an integer and then you do a conversion to the floating point value and then operate on it inside the floating point processor. So these kind of thing can be done using these registers, and you can move the values of the either an integer or a floating point into this registers freely. The processor does not understand or doesn't relate. See, it understands the floating point format, but it doesn't know whether a particular register is holding an integer value or a floating point value. That's only the instructions know. So based on that instruction, if suppose instruction says this is the register R0 and this is I'm talking about BFP R, maybe S0 and S1. This is a convention followed in the floating point. If I say that these two are single precision data and then I operate on a floating point addition, then this bit pattern will be considered as a floating point and this will be considered as a floating point, and it will add these two as floating point and write it into some register S4. It will write in the floating point format. So that's what I'm trying to say here. Okay. So D variants of architecture, these registers can also be used in pairs. So now when I say that, okay, I will show you the registers. So two set of registers, one after the other, can be considered as holding a double precision value. Okay. So there are three or more system registers. This is something to do with the similar to CPSR. There are some system registers to configure the floating point processor as well as to find out what is the flags coming out of the operation of floating point. Those things are managed by some system registers in the system, in the floating point processor. This is the status and control registers. Okay. Now this is the register file. So S0 to S31. Okay. How many? 32 registers. So I told you this is a single precision. That means each register here is a 32-bit wide. Okay. Now what is this? Double precision is a 64-bit wide data register. So it combines S0 and S1 element as a D0. So if you are operating on, if you say I am operating on a double add, suppose if I have a floating point operation, but it is a double precision arithmetic, and then I say that D0 comma D1 parameter, and then D3 is a result has to be written. So it will combine these two registers and access them as a single element as a D0 and then D1 and write the result into S3 D3. So this is how the register files are overlapped with each other. So please remember, this is a physically there is only one. There is no separate physical registers like this and this. Only 32 registers are there. Whether you are considering it as a double precision or not depends on how you interpret these values. Whether you are taking them all together as a double precision or you are treating this one single element as a single precision depends on the operation. So again, whether it has to be interpreted as a single combined as a data double precision data, or it has to be treated as a single precision data depends on the instruction. Okay, as such registers do not have the information whether they are holding either an integer value or is it holding a double precision value or it's a single precision value. The registers do not have any indication associated with them. Okay, one more important thing that I want to explain here, that is called register banks. It is different from bank register that we saw in ARM. Okay, so here the register banks, you have a 32 registers in it, and then if we treat them as single precision registers, they are all listed like this. Okay, there are eight single precision registers here, 8 here, 8 here, 8 here. Now these banks are called bank 0. This set of registers are called bank 0. This is called bank 1 and bank 2 and bank 3. Now what is this arrow indicate? Okay, it is not that these values are all rotated and then they go into the this content goes into this and this content goes into this. It is not that. Okay, please you might have seen those kinds of arrows for rotating bits within the register, but here what it means is, I told you that VFP is a vector processor, right? It works on vectors. Suppose if I give an instruction, okay, fadd, I give an example, okay, S8 comma let me erase it. Okay, S16 and S24. Okay, what does it mean? I gave these registers here. Okay, that's all. Now what am I trying to do? I am adding these two and then result I am putting it here. Okay, assume this. Now there is another apart from looking at this, I mentioned about FPSCR. Okay, I think status and control register. It has got two fields. Okay, let me talk about length field, LEN field. This is a 3-bit pad. Three bits are reserved for LEN. Okay, assume this LEN bit in the FCSR register. Okay, there is only one single register in the VFP, and it has a value 101. What does it mean? It's a 4 plus 1 5. If it has a value like this, okay, 5, then when you do a if add okay, actually it's a convention is that this is the instruction. Okay, when you perform this arithmetic and then you are mentioning these registers and the instruction, while this instruction is being executed by the VFP, please remember this instruction is executed by VFP. It looks at this bit pattern in the FPSR. It sees that it is having, because this one went off, I wrote 101 here. It sees that there is a 5. Then it adds 1 to this value, okay, and it assumes that you are interested in performing not a single scalar operation. You are not interested in just adding S16 plus S24 and writing into S8. You are interested in performing a set of 6 operations, vector operations. What does it mean? You want to do this and then you want to add these two elements and write into this, and you want to add these two elements and write into this, like this goes on up to this. Okay, so the starting point is considered to be these registers. Okay, got it? So if suppose if I tell instead of S8, okay, if I write an instruction assuming that the FPS or values are same, okay, these values are same, I write an instruction saying that S11, S19, S27. This value happens to be the same. That means 6 operation. But you are starting from S11. That means this register S19, okay, and S27. So from starting from this register, go down. If you encounter this end of this, go up and pick the remaining operands. So up to what time? Up to 6. So it will do this. It will do set of this. You know, S27 and 19 will be added and put in S7, and these two will be done and put in this. So how many are done? 5 are done. So one more will be done by taking these 3 in the set. So that is what is called bank registers and how it operates on the bank. And now let me erase this. Now it is not that by chance I picked only these 3. Okay, this bank, remember that it cannot be any register from this bank cannot be taken as an operand or a destination for a vector arithmetic. Okay, you can do vector arithmetic within these 3 banks, but we cannot do from this bank. Now you may wonder what is the use of this? No, are we wasting one set of bank of register itself for this? No, I will give you some examples where we want to do a scalar operation, then implicitly this bank is used for that purpose. So these instructions, these registers are used for scalar operations, okay, and these set of registers in these banks can be used for scalar as well as vector operations. What I mean by scalar operation? Only operating on one register and another register and putting the result back. In a vector operation, we go into set of registers and operate on them. So if you want to perform a vector operation, we can take these 3 bank registers, or if you want to do only scalar operation, this bank register is used. So that's the indication. So register file is divided into 4 banks, okay, 8 registers in each bank, and please remember you can do a floating point vector operation using a single precision or double precision. So if you do double precision, you can have maximum 4 data elements can be double precision can be picked up from the vector. The vector length can be maximum of 4 if it is a double precision operation. And the vector length could be a maximum of 8 in a single precision operation, but it could be less than that, no issues. But maximum it could be 8 because you cannot have a more than 8 vectors, okay, at a time. Otherwise you have to copy from memory and then perform it. I will show you an example where that kind of operation will be done in the end of the class. CDP instruction access the banks in a circular manner, but not load store instruction. That is very important difference. Okay, only CDP, that means what? All the add, multiply, square root or whatever, any arithmetic operations or any data processing operations only act these registers. They only treat them as a bank of registers, because the vector operation what I showed you, okay, they combine and then they operate, give you a vector of data. I told you that, right? So they operate on the vector of data only during the arithmetic operation, not during the memory access. So memory access treats these registers as a set of sequential set of registers starting from S0 to S31, okay, or it treats them as D0 to D15, okay, double precision. So suppose if you want to copy data from memory into the register, you can, based on the length of the copying you want to perform and then what is the starting registers you are giving, up to the end it will go. It will not wrap around. Please remember, loading or storing, load store instructions do not wrap around. They perform operation from starting from a lower register number to a higher register number. It is the same as our ARM processor. Okay, so they don't treat these banks of registers, okay, as a bank in circular manner. They don't treat them or access them in a circular manner. Vector length is decided by the length field in FCS. I mentioned that to you, and then the destination is a bank 0. So another difference is if the destination register happens to be a bank 0, irrespective of what is the value in length field, it will treat it as a scalar operation. I'll give you an example. Okay, suppose you have a f add s. Okay, you say s0, comma s8, comma s16. What does it mean? S8 and S16 is added, okay, and then put into S0. Now this destination register, okay, FD is a floating point destination register, happens to be from a bank 0, right? Is it S0? Okay, sorry, this is not very clear. Let me write it. Let me write it for a change, clear handwriting. S0. Now what happens? Once the VFP looks at this as S0, it will not assume that okay, you want to perform some more operation accessing after this S9, then S10, and then S17 and S18, go on and then perform this. It will not do it. Though length field says maybe 6, it will not do a 6 vector operation. It will only perform a scalar operation. Okay, that is what is conveyed in the last bullet of this slide. If the destination is a bank 0 register, the operation is a scalar only regardless of the value in length field. I hope this is clear to you. Okay, so this is very critical and you should understand this. When I show you an example, you will be able to appreciate it. Okay, let us go little faster here. Loading floating point values into registers from memory and storing floating point values in register to memory. There are these instructions supported. Okay, and then some of these instructions allow multiple register values also. Okay, LDM and similar to LDM. Such instructions can be used to load or store short vectors of floating point values. Transfer 32-bit values directly from BFP to ARM. Okay, register transfer is also there. If you remember MCR and MRC instruction. Okay, these are all the coprocessor register transfer instruction. Coprocessors to ARM register, and then register to ARM register to coprocessor register. So this instruction MRC and MCR instructions are also supported by VFP because VFP is a coprocessor. So all the coprocessor instructions are supported by VFP. Transfer 32-bit values directly from VFP system registers to ARM general purpose registers. Okay, and then it can also do multiple operations. Okay, different kinds of operations on either a vector of data or a single floating point scalar values. Okay, so single floating point values are called scalar. A set of vectors, data elements are called vectors. Okay, that is and then copy a floating point value between registers. So between the register itself in the VFP, within the VFP you can copy them. While copying, we can do a sign bit can be inverted. That means if you want to convert a negative value while copying to another register, suppose S0 to S1 you are copying, okay, and then you want to make it minus to plus. That's a possibility. Okay, you can invert. Sorry, this one is not here. Okay, S0 to S1 you are transferring, but while transferring you want to convert. You invert the sign bit of this. That is also possible. All these instructions also can be used in short vectors. So you can perform these operations on vector of data also. Perform combined multiply accumulate. So you want to do a multiplication of two vectors and then add to the result. Okay, normally it will be kept in another register and then it will be put here. So MAC operation, is a very popular multiply accumulate operation is very popular signal processing instruction, which are also supported by VFP. Conversions between single precision to and data precision, double precision values, as well as unbit, two's complement to sign bit, unsigned to signed also you can do. But you have to remember that if you are converting a huge unsigned value, sometimes it may not fit into the 2-bit value. Okay, because it only represents half of the unsigned value because signed bit is coming there. Compare floating point values in register with each other, okay, with 0. Okay, those compare operations are also there. Now I touched upon exceptions earlier. Let me give you overview. Invalid operation. This is an exception which happens when you do this kind of operation. Okay, 0 by 0. It may generate a not a number. The result will be put as a non. Suppose, see what I mean by this is, suppose you are dividing S0 by S1 and you want to write the value into S3. S3 is what? Single precision register. Now you have mentioned that you want to do a divide operation, but if suppose if it had a plus 0 here and then if this was also having a plus 0, now this is dividing a 0 by 0, which is a not a valid condition. So there are two possibilities. One is it generates an exception, so it goes to ARM and then ARM generates an exception, undefined exception, and then the exception handler, the support code handles it. Or you say that in S3 write quiet nan. So quiet nan is what? This is a one representation, a specific representation to say that I don't want to generate an exception. I want to suppress it by filling in the value with a quiet nan. That means what? This is a pattern which is not a correct floating point value, but it is not a number. It is not actually holding a floating point value, but it is the indication. So whenever this bit pattern is seen by the floating point processor or your application, you should act on it accordingly. So that kind of situation, we can have a quiet nan, okay, can be returned. So it is all, IEEE says that either you do this or you do this. So when we have a VFP with a support code, you can decide whether an exception has to be given or you just fill the. If suppose you get this kind of a division, generate a quiet nan and then go ahead and execute the next instruction. So division by 0, you can either two options are there. Suppose you are positive value, okay, you are dividing it by 0. You can say that there is a positive infinity is representation is there that you can generate and then go ahead with the execution, or you generate an exception. So there are two possibilities. So these are the things defined by the IEEE 754. Inexact. Suppose you are not able to represent a value accurately, then you can round it off because maximum you have a 23 bit of fractional part. So if you are exceeding that limit, then we can round it off, okay, and then store that in the floating point representation. So if whenever you round off, you say that and create an exception, so that if suppose the application developer wants to catch this kind of a scenario, it can generate an exception. And then what are the other different kind of exception? Overflow exception. This occurs whenever you are adding a huge number of floating point values. Either it goes into plus infinity, okay, the addition results in the plus infinity, or it is minus infinity, okay. So in that kind of situation, either you can fill up with this value and then suppress it, or you generate an exception. It based on the application developer's interest, what he wants to do. Now underflow. So let me again 0.0. It was explained in the last class. Anyway, I'll come back again and explain here. See, there is a possibility that underflow can happen. That means you are not able to express this smaller value which you are getting it in the normalized notation. Okay, if you recall, when you are not able to represent in the normalized notation, which is 1.0 into that 2 power e, correct, and then this is f, 2 power f, yeah, 1.f, okay, floating the fractional part. Now when you are not able to use it in the normalized form, you can always say that it is a denormalized notation, and then there is a separate notation for that. That means the exponential portion can be 0, and then fractional portion can be a non-zero. So this can be used if you want to use a sign bit. So you want to have a denormalized number. That means what? You are extending the limit of smaller number to a denormalized value. So you can still extend it either this way, positive side, or negative side. You can extend it into this format. So that can be decided based on a choice. When an underflow happens, if it is too small to be represented in a normalized form, it can be either denormalized or it can be made as a plus or minus 0. Okay, either you can say that it is closer to this and leave it, or you use a denormalized rotation for that. Okay, now exception handling, how do you do it? There are two ways. Untrapped, that means you don't want to trap it, so you this causes the cumulative flag in the FPSR because of untrapped. This causes the appropriate cumulative flag in the FPSR to set the set 1. So if suppose you don't want to generate a trap, then we can the QC flag can be set to indicate that there was a condition which exceeded the limit, but because I don't want to generate a trap, I am just indicating it by setting this flag. Okay, that is the internal handling. Any result register of the exception generating instruction to be set to the result value specified by the standard. So as I told you, suppose the number what you are getting is not 0 is here. The number what you are getting after the division, it becomes too small to be represented. You can decide to put it as a plus 0 or minus 0 from based on where the result is coming from, which direction. So that specific value can be loaded, or you can make it as minus infinity and plus infinity. You can make these values as a result instead of generating an exception. So untrapped is there. That means you don't want to generate an exception. You either do this or you set the values according to the standard. If it is a trapped, you want to generate trap, then this is selected by setting the appropriate flag, and then exception happens, and then the support code will get executed, and who calls the exception? ARM calls the exception. So this is how the floating point processor handles the exceptions. Very good. Support code I already explained to you, a complete implementation of VFP architecture. This is due to existence of trapped floating point exception. Basically, support code comes only when there are exceptions and which needs to be trapped. That means you want to generate an exception. So the support code is typically entered through ARM undefined instruction, I told you, vector, when the VFP hardware does not respond to VFP instruction. So it could be possible that when the operation is not possible to be performed, then the vector processor can say that I don't want to take this instruction. So it will not respond back with the busy signal. Then the exception can be generated, or it could happen later also after the execution also. Handlers can be used for rare conditions. Okay, and wherever the operations cannot be implemented in hardware, the exception handling can be done. So the division of labor between hardware or software is a implementation dependent decision. Okay, so if there is no hard and fast rule that it needs to be done in one way, and then I am just saying that there is a possibility of this VFP causing an interrupt latency to the ARM processor. So you should be aware of that, because ARM is executing in and the VFP is also there. Okay, if you recall, okay, suppose there is a coprocessor load instruction. Okay, load multiple instruction. Okay, what happens? The memory is there. Coprocessor is loading the value from memory into its own register. So if you are clear now, 32 single precision registers are there. So it can decide to transfer 32 into 4 bytes of data from memory in one go. Now this coprocessor load instruction has to be done with the help of ARM, because ARM is generating the address and then the data comes here. So during this time there is a possibility of an interrupt happening, IRQ happening or FIQ happening. Okay, in that case what happens? This existence of VFP, because of 32 into 4 bytes of data is being transferred, this interrupt latency is coming. So don't think that coprocessor is anyway it is running in parallel, so it is not going to impact the performance of ARM. We can't assume that. Okay, so there is a tie-up between them. Because of this existence of this, a particular instruction is getting executed, the ARM interrupt latency may increase. So as a system designer, we need to keep all this in mind before deciding on what kind of instructions you will allow and what kind of interrupt latency you can expect from your system. So, and then other than that, this undefined instruction trap, what I said that your undefined instruction trap is generated by the vector processor, and then ARM is executing it. Now because when the undefined instruction exception is generated, it causes IRQ to be disabled. Okay, that is the default behavior. If we don't enable them internally, I told you one exception handling also where interrupts can be enabled internally inside the handler. If we don't enable them, then this is going to delay the IRQ handling. The interrupt latency of IRQ will be delayed because of this. So that you should keep in mind. So use of VFP in a system therefore increases worst case IRQ latency considerably. It is possible to reduce this IRQ latency penalty by explicitly re-enabling interrupts. Okay, we have to re-enable the interrupts inside the handler to make sure that the interrupt latency is reduced. So though FAQs are not disabled by entry to the undefined instruction handler, it is recommended that FAQ handlers themselves should not use VFP. Okay, what I mean by here, FAQ interrupt can be, they are not disabled even if it is undefined instruction handling of the vector processor instruction is running. During the time FAQ interrupt is happening, then it will be serviced because we are not disabling the FAQ inside the default, it is not disabled. But if FAQ handler itself is using the VFP, then it is going to cause some delay. It may cause a delay because if this instruction which is being used inside the handler generates the vector processor exception, undefined instruction exception, then it is going to further delay the execution. So need to take care that the FAQ handlers do not use any VFP instruction. Please remember, VFP instructions can be used anywhere. Okay, and in that case we have to, some restrictions should be there that handlers do not use those instructions to improve the interrupt latency of the system. Okay, now how does the VFP and ARM interact? I told you that VFP load store instructions are allowed to produce data abort. So VFP implementation are able to cope with the data abort, and as explained earlier, ARM takes care of generating the address. All this you know. VFP decides the number of words transferred by the multiple load store instruction. I am just summarizing it, which you saw it in the coprocessor also, that load store multiple are possible with VFP also in any coprocessor also. Now, and then what are the ARM instructions? Now you know that these are the coprocessor instruction. This is the data processing instruction. This is load store instruction of coprocessor, and this is the coprocessor to ARM register transfer. Okay, and it uses 10 and 11. And then if conditional code is not met, then both VFP as well as ARM treats that vector processor as a instruction as a no op. So one more important thing, I mentioned it in the last class, not last class, in the coprocessor class. So see, conditional execution is handled by the FPSR, the CPSR values in the ARM processor, that is that CZNV flags. So the conditional execution is based on these flags, okay, not based on the VFP flags. VFP also has equivalent flags, but it is not based on this. Suppose you want to execute some instruction based on this conditional flag, this needs to be transferred to the ARM CZNV and then it should be performed. So there is a provision for that, that is called FM stat instruction. What does it do? It transfers the floating point status register values into the CPSR register. So how do you do it? We perform this C to R, and R will be R15. No, we give that, no, the target register is R15 in ARM, and then we say that FPSR value, SCR value. Then what happens is the lower 4 bits are transferred to the CPSR. Okay, that is how it is done. I think I explained this in the previous discussion, so we don't have to go into the details. Now we are going to conclude this class with one small example, which you will love it. Okay, let me explain this now. Don't get overwhelmed with the instruction and no length of instruction. It is going on so big. See, nothing, F is nothing but it's a floating point. LDM and STM, you recognize it very well. Okay, the load multiple is not IAS, it's not the government service. It is increment after. Okay, it is a stack operation or a multiple data transfer operations. Okay, it can be used for anything, but it's a multiple data transfer operation. So we want to say that memory, you increment it after loading this value, whatever the current base pointer is pointing at. Okay, if you recall, and then S is to indicate that this instruction will be modifying the flag. Now this is the base register. Base register has to be a ARM register. Okay, because address generation is done by ARM, and then the base register is getting incremented based on this condition, and then it is a load multiple. Load multiple is what? It is loading into register. Which register? The floating point registers, S8 to S15. Okay, so basically what is happening here, a set of 8 float values, the 4-byte values are copied from memory to the registers in the processor. Okay, inside the floating point processor. So this whole thing is understood, and then it generates a coprocessor instruction. The assembler would have put a coprocessor instruction to give this information to the ARM and coprocessor, and they work in hand to transfer this value from memory to the coprocessor registers. So now what happens in this instruction? A base register R2 is used, and it is written back. The incremented address is written back, and then it is copying into this set of registers. Now 2 set of registers are copied. Okay, let me go to the next one. So what happens is, you see memory. Okay, if you understand this, then you will know how floating point processor works. Okay, VFP. I have a vector set of registers. Okay, S8 to S15. Okay, this is what it belongs to. Which bank? Bank 1. Bank 0 is S0 to S7, so that is not used. A bank 1 is used, and then another bank is used, S16. Let me change the color. Okay, S16 to S23. This is how many registers? 8 registers are there. This is bank 2. Okay, now it is copied from, see, ARM is here, and then 2 registers R1, R2 are there. R1 is pointing some location. From that address, increment after. So this is lower address. Suppose this is lower address and this is higher address. It is incremented and then it is fetched. And R2 is pointing to some other location in the memory, and that is fetched. And this data comes here. This data goes here. So ARM is generating the address, and then data is going into the VFP. Okay, it is not coming back to the ARM processor. It is going to the VFP because it is a coprocessor instruction. Got it? Okay. Now what is happening next? I think you understood these 2 instructions. Now let us see what is this. F add as S24. Okay. Now S24 is coming. Only S24 is coming. Okay. I am sorry. I am exceeding the limit of the processor. Assume that the processor is bigger enough. So now S24 is here up to S31. Now this is bank 3. Okay. Now assume the FCSR value. Okay, that is very important. That time, see, when this instruction is to be executed by the floating point processor, it looks at the FPSR LEN field and sees that, okay, I have a value which happens to be a vector of length 8. Okay, that means what? Whatever value is here plus 1. So vector of 8. That means it is supposed to do vector arithmetic. What I mean by that? S16, starting from S16 and starting from S8, which have the data, already you have loaded them with all the data. Okay, you perform the arithmetic. Like that means what? S8, okay, is added to S16, okay, and written into S24. Now don't stop with that, because this is 8, 7 plus 1 8. So 8 operations need to be done and in sequence. That means S9 will be added to S17, okay, and right into S25. Go on like this, and then you do a S15, okay, plus S23 and right into S31, okay. So who does this? We are not given any of these register values. Only this register values are given, and it is implicit that if it belongs to the different bank other than bank 0, and the LEN field says how many elements in a vector operation to be done, then that many operations are done. This one instruction performs 8 additions. Okay, remember. Now let me erase the whole thing. No harm. You remember these banks now. Now you see, I wanted to show you one more example of a scalar operation. Here again the bank, okay, there are two banks, okay. The input banks are S8 to S15 and S24, okay, okay, into S1. S1 belongs to which bank? It belongs S0 to S7 belongs to bank 0. So if one of the operands, especially the RM operands, okay, this is RM operands, RN and RM, if you remember in the ARM days. So this is a scalar register because it belongs to the bank 0. Okay, then this instruction, though this LEN value is not modified between these two instructions, okay, it remains to be 8, but it will do a scalar operation. What I mean by scalar means it will not, when it sees S1, it picks only the S1 value and then it multiplies with everything in S8 and then writes into S24. That means it will say S8 into S1, write it into S24, okay, and then S9 into S1, same register, please keep in mind. That will be written into S25 and so on up to S31. S31 is written into by S15 into S1. So that actually you are doing a scaling operation. You are performing a scaling operation by fixed amount of S1 scaling. You are doing it on 8 data. Actually speaking, it is a vector of data, but one of the element is a scalar. So that multiplication, why multiplication? It is a multi instruction. If it was an addition, everything would have been added by S1, otherwise multiplication. So this is one flavor of another instruction. I just wanted to show you that a VFP instruction can be written this way. Now what happens? Okay, we have done some job inside the VFP. Unless this value what is computed comes out into memory, there is no use of this operation, right? Then only once it comes into memory, maybe ARM can do something with that and then can perform something on it. So you have to get out the value what is there in the internal registers to the memory. So that is the STM, store memory, store in the values from register to memory, and the results are in S24 because this is the register bank which is holding the register. So you have picked up all the 8 registers, and then R0 is pointing to another location in memory where it is copied into. So that is done, and then now I am showing you one more. Subtract R3. Suppose R3 is having a count of 8 floors. That means suppose you have, okay, multiple sets of values. It's not only 8. You have some 80 values. Okay, that means a set of 80 values in another. The R1 was pointing in one address, and then R2 is pointing to another set of values. Okay, both of them are having 8 floating point values, single precision. Okay, 4 bytes each. Now we have performed 8 data we have taken from the memory, and then we have multiplied and we scaled and then wrote it into another location which is pointed by R0 we have stored the 8 set of values. Now you want to take up next set of 8 values from here and there, and then perform the operation and write into next set of results. So how many times you will do? R3 will be, the count will be initialized with the 10. So you perform 10 times this. Okay. So because the registers are limited to only 32, you can't have infinite registers in the processor. But you are interested in performing, a set of 80 floating point values stored in 2 locations, and then writing the set of 80 values as a result. So you can do it in 10 times, but that control is done by this. Now where is R3? R3 is an ARM. Please remember, ARM is having the value, the R3. Okay, so it is looping back. The looping back control is done by whom? ARM processor, because the instruction sequence is controlled by ARM. Now what happens is, after this execution, because this subtraction is done in the ARM processor, please, this instruction is an ARM instruction. You have to keep in mind which are floating point instruction, VFP instruction which is done by coprocessor, and which are ARM instruction. So when ARM instruction is done, the BME is what? Branch not equal to, that means this is subtracted by 1, because one set of values are done, and then if it is not 0, then you want to go back. Now this instruction is coming again. You may wonder what happens if my coprocessor is busy with the previous execution. VFP is busy with the previous loop. Now I am giving another floating point instruction. If you recall, ARM processor will send a NCPI, then floating point or any other coprocessor will say that I am present or absent, and then whether I am busy or not. So if the coprocessor is busy with the previous loop, it may not take this instruction, or it may not take this instruction, because load module might be free, it may do that, but it may not take this instruction if it is busy with the previous add or previous mult. So effectively what will happen, ARM processor will block, the pipeline of ARM will stall in the execution, because the coprocessor instruction is not taken up by the VFP. Okay, so there is no need to have any other mechanism of waiting. The waiting is implicit, because that is a condition that ARM processor has put in. Unless the instruction is accepted by the floating point processor, do not go ahead with the execution. So the ARM processor will not go ahead, so it will get blocked, because this instruction will be executed faster. This also may be done faster, because ARM is doing this and is a small integer arithmetic, whereas these are all floating point job. So it will get blocked when multiple iterations of this has to be executed. This you should keep in mind, how the whole thing is functioning. You have to have an understanding of VFP, you have to have a understanding of how this handshaking is happening, how ARM is generating the instruction addresses, how these registers are controlled, and which CZNB is used. All of these things should come in your mind when you try to understand this flow of instruction. Okay, so I hope this explanation was clear to you. So this is a typical example of how a floating point processor could be used for processing a set of data. Okay, so we have come to the end of this class. So we have covered all of them. I am very happy to share this very interesting part of information. So we covered ARM instructions, and then now we have covered the coprocessors. Now we have completed coprocessor. Now we are going into travel outside the ARM. So we have come out of the ARM, we went into coprocessor. Now in the subsequent classes we will roam around the SOC. Okay, you know that SOC has ARM processor and coprocessor. Okay, some memory. So we will visit all the friends in the SOC. Okay, as a part of the different units will be covering those things. So see you in the next session with some other interesting topic. So with this we are completing the coprocessor related instructions. So I explained you the coprocessor interfaces, and then I explained you coprocessor instructions, and then now I showed you how a VFP is implemented using the coprocessor interface. okay, using the coprocessor instruction how a VFP is implemented. Before that we saw how floating point is represented. So now we have covered all of them, all the related topics of coprocessor. So we are ready to get into some other interesting topic in our journey towards ARM SoC design. So I'm very happy to share all this information with you. These are the reference books. Okay, more often I will be using this. Okay, and this is also being referred, and of course ARM manuals are used in all the lectures. Okay, thank you very much for your attention. I hope this was useful, and talk to you in the next class. Bye bye.